official class stuff. So on Monday, there's another one of these workshops coming up. You might want to go to that. It's worth extra credit. Kate Kligman will come in and give talks about how to do open source security research. And you can also connect remotely. But if you show up, last time they had pizza, I'd imagine they'll have it again. Yes, and the question, Eric, yes, the LLMs are absolutely not neutral. It's the Grok LLM is the far-right LLM. It's trained primarily on Twitter, and Twitter is now mostly Nazis and far-right people, so it's all full of lies of that sort. Most LLMs are trained on a huge amount of data they just found on the internet, so they also included Fox News and Breitbart, and so there's maybe 10% corruption of complete mythological lies. But there are some AIs that are actually carefully trained on trustworthy data, like they go to a trustworthy medical source and train it on high-quality medical data. But those are the large ones are just trained on a giant pool of data, and they do adjust them. They can adjust them in various ways, and they're trying to adjust the Facebook one to appeal to lunatics on the right. Anyway, oh, by the way, there's another hacking club coming up a week from Saturday, so it's remote. You can tune in on Zoom. That's also worth extra credit, and it's probably of greatest interest to students in 123 and 124. But anybody's welcome. Dave Porcello has done a few of these, and he's back again. So check those things out if you like. And all right. So we're talking about kernel debugging today. So Ollie Debug is the debugger we've used, and Immunity Debugger, that's essentially the same thing. And those are nice for user-land debugging, but you can't debug the kernel with them. The only ththing that can debug the kernel is WinDebug, as far as I know, which is from Microsoft. And it is fabulously difficult to use. It uses one of the more difficult interfaces of Microsoft, and we'll show you how to use it. It reminds me of IDA Pro. It's just not simple to use. But anyway, so the device drivers are a huge problem for Windows. If you make some piece of hardware, like a fancy mouse or a printer, then the manufacturer of the printer has to write a driver which will send the correct voltage signals to that device to control it from Windows API calls, and that has to be in the kernel. So there is non-Microsoft code in the kernel. Now, Microsoft really doesn't like this, and when they put up Windows XP had an error reporting tool added. They found out that more than half of all the blue screen error crashes are caused by third-party device drivers, because they're typically, especially if you buy cheap hardware, the drivers are written very sloppily and very badly, and they crash. They'll often take the driver from a much earlier version of Windows, like Windows 95, and just run it without updating it properly. So it doesn't really run well in modern versions of Windows and things like that. So this is a problem. Now, applications don't directly access, they access these things called device objects in userland, which are used to send signals to the device driver, which lives in the kernel. So devices in the Microsoft land are not physical hardware component, they're software representations. So a driver creates and destroys devices, which you can then access from user space. These are Microsoft terms worth knowing. So if you plug in a USB flash drive, the operating system detects a new piece of hardware, and then it creates the F device object. Now applications can read and write to F, and they will be sent to the driver for that USB flash drive. If you plug in a second flash drive, if it's from the same manufacturer, it probably uses the same driver, so it will reuse the same driver and create a new device called G to refer to the second flash drive. All right, now remember how DILs work. DILs are libraries. They're loaded into processes, and they export functions using the export table. When you load a library, it calls DIL main. DIL main is the preparation function that prepares the library for use. So that's what DILs do. Drivers are similar, but drivers are loaded into the kernel. And when they're first loaded, they run the driver entry procedure, which is the analogous thing of DIL main. It's the thing that prepares it for use. And this prepares things called callback objects, so programs can use the driver. So there's some stuff about how it defines a callback object through which other drivers can request notification of conditions and so on. So, all right, so DILs load into memory and execute DIL main when they load and have use an export table. Drivers load into the kernel and execute driver entry and prepare callback functions and callback objects. They are analogous, but different. So driver entry, drivers don't expose functionality through the export table. They have to register addresses for these callback functions, and that's what the driver entry routine does. And then the Windows will create a driver object structure, which is used from userland to call that object. the device. All right. So a normal read request, you will obtain a file handle to a device. You'll call read file on that handle. The kernel will process read file and invoke the driver's callback function to communicate with the thing you're trying to read from, like a modem or a hard drive or something. So the most common request from malware is device I/O control, which is a generic request. And you can then send some data in, send or receive data from a device with this generic request. So here is how user mode calls are handled. You have your program, it calls kernel 32, it calls ntdil, which is now remember kernel 32, the general rule in Microsoft is everything is always named the opposite of what it is. So kernel 32 is not the kernel. It's the user land gateway to the kernel. It then calls ntdil, which is the native API, which you're not expected to use directly. You're expected to use it through kernel 32. That then calls the kernel. This is the real kernel, ntos kernel.exe. And that can then communicate with a driver to get to the hardware, but it can also go through a malicious driver if they manage to get a malicious driver into the kernel. And this is a fairly common form of attack now, and then take malicious calls. All right, and there is some, or at least there used to be kernel mode malware with no significant user mode components. Now, these days, Microsoft requires drivers to be signed in almost all versions currently in use of Windows, which to try to prevent people using malicious drivers. But the problem is what the bad guys have done is they have found drivers that are signed from versions of products that were found to be defective and have vulnerabilities, and they call this the bring your own vulnerable driver attack. It'll install the driver, which is signed and accepted as a acceptable driver, but it is known to have a vulnerability, and now they can exploit that vulnerability. All right. Malicious drivers don't usually control hardware. They interact with NTOS kernel and hal.dil, and they can import functions from these to manipulate the kernel. All right, let's try a Kahoot. There's a lot of terms in this one, so I added a lot of Kahoots to review them. 10A is here, and let me move that in. There we go. Two players this time. Ah, good. 3 is better. 4 is even better. Actual competition. Good. All right. All right. So what can an application directly interact with? This is where, like I say, Microsoft terminology could make you cry. It can interact with the device because it's not allowed to interact with the hardware. And a normal person would think those two things are the same, but in Microsoft land, these things are very far apart. Device is a user land software representation of something that will eventually go to hardware. It's pretty stupid, but that's the way it is. All right. All right, what code is loaded into a process? DILs load into processes. And I remember, boy, when I first studied this stuff, this is my hardest class, this is 127. Windows is pretty confusing. There are so many strange pieces of Windows flying around with technical terms. It takes a while to get used to them. And that's why there are so many vulnerabilities. Windows is really complicated. There are a lot of different software objects interacting. A lot of them are out of date. They don't communicate with each other very well because Windows is like the Frankenstein monster. It was built by patching together all kinds of stuff, often purchased from third-party companies. So it's a bunch of things all patched together to make this assembly. So, it takes a long time to get used to all the pieces that are on Windows. It's really important, though. All the large corporate networks must use Windows because of all those rich features. It has the features to handle the problems you get on really large networks, which Linux does not have. Anyway, so I encourage you to stick it out and get used to all this terminology. At first, it seems overwhelming, but if you go through it enough times, you get used to it and you absorb more of it. All right, when a driver is loaded, what procedure is first called? The driver entry is what starts the first thing you call to prepare a driver for use. All right, which one of these runs in user mode? There you go. Like I said, the way to learn everything in the world of Microsoft is everything is named the opposite of what it is. So the one that does not run in kernel mode is the one named kernel. Like I say, you get used to this madness, but at first it just seems very cruel. Anyway. There. I think these probably are. I'll have to tell them who they are if they want to finish. Anyway, all right. So kernel debugging is what you do if you want to debug problems in the kernel, like problems with device drivers. You have to somehow get a debugger in there, and that's not easy because remember your debugger runs in user mode typically. It doesn't have the privileges to get in the kernel. Now in VMware, you can do this by first you enable kernel debugging in the command line with bcd edit, and then I actually had students doing this maybe 10 years ago. You would now have two virtual machines running Windows, and you connect them with a virtual serial port. This is the way you really get full control of the kernel. You have two machines, one controlling the other. Now you can put a breakpoint in the kernel so the kernel stops, which means that machine is frozen. It won't respond to the keyboard or the mouse or anything. It has to be remote controlled by another machine. For full functionality, that's what you have to do. You have to have two machines connected by a cable. And until recently, that had to be an old serial cable that doesn't even exist on most modern hardware. Then they made it possible to connect them with Ethernet, which is somewhat better. But anyway, I'm not doing it this way anymore because this was really too hard for students to set up. It was the source of great suffering, getting these virtual machines to connect through a virtual serial cable. And that was, in the old days, in Windows XP, we had this thing called boot.ini, which you would use to control whether the machine is in debug mode. But now, all modern versions of Windows use bcd edit for boot configuration data. You enter in an elevated command prompt, you say boot control edit /debug on, and that will put your machine in debug mode. By default, machines do not allow you to debug the kernel at all, because it's not something a normal user would ever do. But if you do this, then it enables it for kernel debugging. And then, now these days, you install WinDebug, and WinDebug has gotten much easier to use and much more powerful. And so after you install WinDebug, which is actually much easier, you don't need to go through this anymore. You go to my link, it's just an ordinary download now. Microsoft has simplified it. We used to use this thing called LiveKD, which is something Mark Russinovich wrote that makes a crash dump of the kernel, and then you analyze the crash dump. So you can analyze the kernel without using two machines. But as you see, we don't need to do this anymore. This is no longer necessary because Microsoft replaced this old WinDebug with a new WinDebug, which is now the standard. It was in preview mode for several years, but now it's the standard, and you'll see it in the projects. And it can do direct connections to the kernel. After you enable kernel debugging, you can examine it. Now, you can't put breakpoints in the kernel, but you can use it to debug userland, and you can at least examine the kernel. So WinDebug, like I say, has this interface which is pretty confusing. Now let me bring up the projects that's going to show you the modern interface, because these slides have the older interface, and I want to show you what it looks like. Here's 430. Here's what the new WinDebug looks like. There. It looks a little bit friendlier, but it isn't. This is deceptive. In fact, okay, this is what it looks like. You have a ribbon, so it looks like Microsoft Office, and you have these friendly buttons, but they're all a waste of time. They really don't work. What you have to do is put in command line commands in this little box here and get the output there. I don't know why they bothered to put a GUI on this at all. In my opinion, they should have just left it a command line utility like GDB. That's what it really is. And to get anything done, you have to use command line commands down here that you have to learn. But they added all this GUI stuff to give you the illusion that you can use it with a mouse like you use Ollie debug. But that is not true. Almost none of these mouse gestures actually do any good. So the real action happens down here in the command line. And that's why people find it hard to use, because the syntax of the commands is pretty screwy. It takes some getting used to. Anyway, we're going to learn a few of the simple WinDebug commands here. So D will display memory. You can display it as ASCII, Unicode, double words, or so these are ways to display text. E will edit memory, which I have never done. You can only do that if you actually have two computers connected together and you're modifying kernel memory, although you can use this to edit memory in userland. And then you can do arithmetic operations. GWO will reveal a value at a 32 location pointer. So what you can actually do, I haven't done this much, but I've seen people write scripts. You can write a whole script in WinDebug that will set a breakpoint, run to the breakpoint, then take the register, calculate an address, load the address, put it here, and then go around and around. So you can make something that, for example, if you have some process running that is touching a lot of files, you could make a script that will print out the name of every file that it processes by noticing when it calls a create file API call and fetching the parameters to the API call and printing them out. But it gets pretty complicated. BP sets breakpoints. G is how you start it running again. So here's a combine command that will set a breakpoint at get process address. Then it will print out the second argument. This will display ASCII, the contents of ESP plus 8, which is going to be a parameter. The second parameter fed into it, and then it's going to go again. This is a script that does all this in one line. So you can write scripts like that. In the projects I'm giving you, we're not doing anything even that complicated. We're just doing one command at a time, because we're just scratching the surface of the easiest stuff to do with WinDebug. But the pros write these complicated scripts and can get it to do all sorts of powerful, fancy things. So, like I say, no breakpoints with live KD or with the kind of debugging we're going to do here, because you're not really debugging a live kernel. There is no way to debug the kernel that you're using. You have to have two Windows machines. It's the only possible way to actually break the kernel. All right, and you can list the modules here. So if you'll see things like list modules, will list all the modules. You can specify you want to see just the disk, and then you'll see the disk driver, which is, all right. And you can read from memory with DD. This will show the start of a module, and this will show the first 10 words. A lot of the commands are like this. And when we get to the hands-on, you'll practice with some of these commands and see how they go. Here's DDNT. It just shows a raw hex dump, just like what we've done in GDB with x/8x. And here's limiting it to only do 10. 10 is hexadecimal, and it's that many 32-bit words. That's why it's printed out 16 32-bit words, not just 10 addresses or anything. So, all right. The main thing is there is a help button here's the most important. The only thing that is worth anything in the GUI is this thing, local help. When you click that, it will open an old Windows 3.1 chum file help page, which is the real documentation, and this is where you learn how to use WinDebug. This is where it explains all the options and how they work, and you always have to go back to this. The commands are confusing, and this is where you learn it all. No place else. So we'll do a little bit of that in the hands-on project, and you'll learn a few commands. And R will dump the registers, which I've never used either. But anyway, you've got those options. So let's try another Kahoot. And let's see, which is these cahoots? No, these are cahoots. There we are. 10B. All right. Have only 3. All right, so which command will set a breakpoint? BP, that one's pretty obvious. These commands are in this form are actually not too confusing. All right, which one will show memory contents as ASCII characters? D for display ASCII, GA, all right? All right, which one will show kernel drivers? LM shows the loaded modules, and kernel drivers are among those loaded modules. Those are the components in the kernel that are running. And which command will change memory contents? Will edit memory contents, although, like I say, you can't do it in the kernel if you only have one machine, but you can do it in user land. All right, so let's talk about symbols. This is a big issue in all debugging. If you have an executable program like Microsoft Word, you usually do not get the symbols. They compile it and they strip out the symbols for 2 reasons. The symbols are the names of the variables and the names of the methods and functions and subroutines. There's 2 reasons to strip them out. The first thing is it makes the file smaller. The second is it makes it harder to reverse engineer the file. You don't know what the variables mean, you don't know what the functions do, you have to read the code and figure that out. So it is typical for everybody, commercial software writers and malware writers, to remove all the symbols. Now, if you are developing your own code, you typically want to compile it with the symbols in there while you're debugging it to make it easier to debug it. And if you have symbols, instead of somehow finding the address of a function, you could use its real name like this, create process address space, or you can alphabetical name. Those are symbols. And so Microsoft does provide symbol tables for some of their software. So you can add it, and that makes it easier to debug Microsoft operating systems. You can search for symbols. If you give the name of the module, bang, and then the symbol name, it'll look for that symbol in that module. And we'll do a lot of this. This is quite helpful. All right, and the module name is the name of the file without the extension. It's an exe, dil, or sys file. All right, and so ntos.kernel, for example, is one, and you'd normally expect this to be named NTOS kernel, but since it's the kernel of the operating system, you refer to it all the time, it has a short name called NT. It's one of the few exceptions. So you can do an unassemble of NT bang, NT create process, that will go into the NT module and find the label called NT create process, which is the start of a function, and it will unassemble it, showing you the contents of that. So there's ones to try here, and let's see, I wonder if I got my Windows machine going. Let me get it going here. All right, and all right. Oh, that's right, I was doing another project here. Okay, so here's my Windows 11 machine, which seems to have crashed badly on me. All right. Let's see if it's not going to let me do anything. Okay, let me get rid of it. Shut down. Shut down it goes. It should do it. Cannot be shut down. All right. Well, this is annoying. I may have to kill. Let's see, how am I going to get rid of this? Window, virtual machine. Okay, it finally stopped. Good, there we go. Blue screen of death. That's cool. Okay. Haven't seen that in a virtual machine in years. That's good. So that's what happens when something goes wrong in the kernel. You get the blue screen of death. Now, I don't know what caused that, but I do know I was trying out a bunch of Metasploit malware on that machine. And apparently, I found one that crashed it. Okay, now it's going to put on Windows updates or something. So we'll just carry on, not try to demonstrate things right now here. Anyway, here's what you get if you unassemble NT create process. You get the code. And this is on an Intel processor. These are Intel assembly codes. And here's the raw hex bytes. So you can see that assembly code. So you can do, you can set a breakpoint. And BU is a deferred breakpoint that will put a breakpoint on this when this module is loaded. This is a function that finds the entry point of a module. So this will put a breakpoint on the entry point of a driver. So as soon as the driver is started, it will immediately break. This is kind of useful, although I've never used it for anything. I've never done anything that complicated, but that is a reasonable thing to want to do. And you can search. X is the #1 command. Remember, I've told all the students that use command line, every other command should be ls or dir in Windows because you have to see what's going on. And X is how you look in the kernel. So this looks in the kernel itself, NT, for star create process star for labels that have create process in them. So it will show you all the internal functions that have to do with creating a process. And you can look for the closest symbol with LN that will look to this address and then try to find any labeled locations near there. So I can go to this address and it finds there's something called NT read file there nearby. And there's another one called NT read file scatter nearby. So that can help orient you. This is why I say you can totally hack the kernel for Windows, then the API for Windows, because using WinDebug, you can see how it works. You can take it apart and understand it. There are no real secrets. People say Windows isn't open source like Linux, and you don't have the source code, but it's not impossible to understand it by using the debugger. Anyway, so there's a lot of undocumented internal types that were only intended for internal Microsoft use that malware uses, and you can see the structure of objects with DT. And so here's an example. If you do DT NT driver object, this will show you what drivers look like, and they are C++ data structures. They have a type and driver extension, and the name is a Unicode string, and so on. And here's the number of bytes in each one of these pieces of it is. This is a standard data structure. And so I might be able to try some of these. Let's see if I can get in my machine yet. We'll see. All right. Let me see if I can fit it on the projected part of the screen. Looks like that's working. Okay, so let's launch WinDebug. There it is. I think I'll run it as administrator. All right, and I've turned on kernel debugging on this machine, so I can actually connect to the kernel here with attached to kernel, and then local here. So it'll put me in the kernel, and there we go. It's loading. So all right. So I can, for example, look at the loaded modules with LM. And it'll show me, here's the loaded modules, here's NT, the kernel itself, and that's the only module where I have symbols. Microsoft gives you the symbols for the contents in NT. These are other parts of the things that are running in the kernel, but I don't have symbols for them, so I'm just going to see raw code and numbers. So I can now look for things like create file. I can do examine for NT bang. If I do everything, it'll be a really long list, hundreds or thousands of things. But if I do things that have the word create file in them, it'll be smaller. All right, that's a smaller list of maybe 10 or 20 things. And you see there's various objects, and these are various versions of API calls that create files. And if I could, here's one called ZW create file. And I've just found the symbol with X. I could unassemble it with U. And now I'll see the contents there. It turns out this is not a function, it's just data. So I'm seeing data here. Addresses are stored. I'm seeing the contents of the addresses, and here's assembly language instruction, and here's a pointer to another service. Now if I go to IO create file, I think that's actually a function. So if I unassemble that, all right, let's see. Yeah, that's a function. So now you have assembly language commands and the hexadecimal version of them, and here they are. These assembly language commands, though, are ARM assembly, because I'm running Windows 11 on ARM. So they look somewhat different than Intel commands. The main difference you'll notice is every command is exactly 32 bits long. ARM assembly commands do not vary in size the way Intel assembly commands do. Anyway, so that's a few things you can do, and I think I wanted to do, looking at a driver object, let's try DT, driver and device object. Let's take a look at this one. Okay, so there we are. So this is why I say you can learn what's going on in Windows. You can learn how drivers work. Here's the structure of all the drivers. They have a driver name, there's a string, and then they have something, a hardware database, and all these. You can learn what these things do. You can see the code that's going to use it. And you can also see what a device object looks like. If I change this to device, here's what devices are. Remember, drivers are the kernel object to control hardware, and devices are the user land object to control hardware, and here's how that looks. And again, it's got something called a device extension, and no readable strings apparently or anything, but this is the stuff you have about it. Anyway, so you can look at all the pieces and figure out how Windows works. And there's a great book called Windows Internals, 2 books by Mark Rusinovich that goes all into this in great detail and is really sort of the more advanced version of this course. We're doing just the basics of looking in Windows. You can go much, much deeper. And so here's the beep driver, for example. You can look at the driver object. I don't know if they still had the beep object was used in MS-DOS. If you type Control-G, it would go beep. And it's been in Windows for years. I wonder if they finally got rid of it. Here's the information for the beep driver. I think it's gone. I used to use it in projects. I think they finally took it out. Let's try examining NT bang star beep star. There's still, yeah, there's nothing in beep anymore. Yeah, they finally got rid of it. It's been a hangover for many versions of Windows. Anyway, so driver init is what it calls when a driver is loaded. And so you can see in the code here, here's driver init. If you get into the structure of a driver, there's going to be an address to the driver init. All right. And malware sometimes will put the entire payload in there. And as we've done in projects, you've seen that if you make a malicious DIL with Metasploit, it puts all the malicious property in DIL main, which is pretty unprofessional. Then it will run the attack, but it will not continue to load the driver. That's why we had a project back a while where you made a real driver that did a man-in-the-middle attack to allow you to continue, a DIL rather, a DIL that would let you use the real DIL behind it and add malicious content somewhere more intelligently than in domain. But anyway, you could put your malware in driver init, and that might be all right. It will run your malware as soon as the driver is loaded. Now, if that's the only thing your driver is for, it might be okay. But if it's a driver that's actually being used to control hardware, then it will break that part of the program. You can never get further than that malware part, unless you write it carefully so it can proceed through it. Anyway, all right, so if you're connected, you can configure WinDebug to automatically download Microsoft symbols. I haven't worried about this. It seems to automatically now include the important symbols, and you don't have to manually load the symbols, which you seem to have to do deliberately in earlier versions of this. The latest version of WinDebug is more convenient to use. You'll see that in the projects. In just a few minutes here, let's take a look at another Kahoot, 10C. I think the GUI features are worthless, but it has become a little bit more user-friendly to use. And I think a lot of Windows users never want to use the command line at all. But I think nobody should be running a debugger unless they're ready to use the command line. Anyway. There are huge disputes about all these things, like which editor is best and such. These are matters of religion. All right. All right, so which command will set a breakpoint? Oh, okay. That's right. I thought we were duplicating one, but we aren't. Yeah, this is the one. This is a conditional breakpoint that will hit the driver entry on this, well, the entry point of this object when it loads. That's a deferred breakpoint, BU. All right. All right, which command will show the type information for a structure? Yeah, DT displays type, and this is a class, a C++ data structure, which contains a series of fields that are used to represent all the information about an object. That's object-oriented coding, and that's, of course, used in Windows. It's written in C++ using object-oriented coding. All right, and which command will list all the functions in the kernel? This one does, technically gives you more. It gives you all the symbols in the kernel, which is all the functions and all the labeled areas of memories for storage of data also. But it will give you all the functions. Everything starting with NT bang, every symbol in the kernel. All right. So, we got a little bit more before we get to the hands-on stuff, which is working well. I got them all tested today. So in practice, if you look at a program that writes to files from kernel space, that's an unusual thing to do. Normally, you don't write files from kernel space, you write files from user space. And kernel mode programs cannot call user mode programs. That is an interesting thing, and I don't know why that is, but in the kernel, you can't call user mode programs. So it can't call create file and write file. It has to use the kernel version, nt create file and nt write file. So here's the code. This is going to call creating a service with the create service function here. And the service type is here. It's a 1, and that is a kernel driver. So this is going to create a kernel driver in user space. And this is going to prepare all these things. This is going to create a file, obtaining a handle to a device object. And then this one here is going to have, it has a handle. It uses device I/O control. Remember, that was the generic call that malware often uses to send data to the driver. So here it is calling device I/O control, and all these pushes are loading the parameters on the stack. So you see the number of bytes returned, the buffer size, the control code, the handle to the device. That's why this generic device I/O control can be used to read or write to any device. You have to first obtain a handle to the device and then pass it in, and it will then use that to indicate which device you're talking to. So you can set WinDebug to verbose mode, and then you'll see every kernel module that loads. Generally, loads are suspicious. You shouldn't be loading things to the kernel while you're running. Although, if you're in a virtual machine, there is one thing that K-mixture will keep loading and unloading as part of the virtual machine. That's not suspicious. But normally, when things are loading in the kernel, you don't expect that to happen while you're running. You only expect it to happen when you boot up and it detects new hardware, or perhaps when you plug in something new like a USB stick. But under normal conditions, there shouldn't be anything loading or unloading. All right, and so bang drive object will show you a driver object. You can give it the name. So here's something called file writer, a loaded driver, and it will show you some information about it. Now it's going to warn you that it does not have the symbols for this, so it's just going to give you addresses, but you'll get the structure of it. And here's what, we've looked at this before, this is what a driver object looks like. It gives you sort of the same map you'd see if you looked in the C++ source code in the start of the file, where it declares the structure of objects. It just tells you what type of data is stored. It gives you names of what they mean because you have symbols for the kernel, and it gives you what the current value is, I think. All right, and this is the file writer object. You see the Unicode string shows driver file writer. So this is that file writer driver that we're looking at in there. And so if you trace this function, it eventually creates a file. This is a fully qualified object name. You know, normally when you write a file, you write it to C:\/ folder name, file name. But if you use / DOS devices /, then you're actually identifying the root device of the system. And this is something people do quite a bit to do things like wipe out a whole disk, including the partition table. You do a raw access to it using these kind of handles. All right, so applications work with devices, not drivers. You look at user space applications to find the device object, and then you'll find the driver object in kernel mode. Dev object will get you more about the device object, and you can find handles. The handles will be handles to that, which are being used to refer to it by code. All right, and then we can talk about rootkits, although I'm going to skim over it quickly because the rootkits I'm talking about here are the old-fashioned rootkits. They're hard to make now, and I do not know how modern kernel rootkits work. I've tried to figure it out a few times. It's pretty mind-boggling. I don't know how common kernel mode rootkits are, but here's the way they used to work. The point of rootkits is to take over your machine and hide a bunch of its operation so you don't see it anymore. It'll hide processes, files, network connections from everything, including your antivirus. It'll make a folder and hide it so you won't see it. And even if you do directory, you won't see it, and your antivirus won't see it, so it won't notice malware running in there. And the most popular way this was done up until around Windows Vista was this SSDT hooking. And I used to have hands-on projects where you do this. This is also how a lot of anti-malware products work, like Zone Alarm Firewall. What you do is when the user space calls the kernel, it calls one of these commands, syscall sysenter or int2e, and this will go into the kernel, and it goes through the system service descriptor table. And we're manipulating the analogous object in the projects in Linux in 127. And so you enter here with sysenter. So here's how you get into you move something, you call sysenter. And the EAX you load here is the code that tells it what kernel function you want to run. And 25 is NT create file. So this is how you create a file. You prepare EAX with the right code number, and then you load some other parameters like the name of the file and such, and then you call sysenter, which will set the call number 25 in there. Now, that goes into the kernel. Now, the problem is Windows might update, and the addresses of those kernel objects might change, but your compiled userland program is not going to change, so it's going to try to find them at the old address. So you do not directly call the addresses of kernel files. Instead, you go through this lookup table called the SSDT table. So when it wants to go to NT create file, it goes to the table, to 25th entry. That's what the code number is for. And this then points it to the function. And if you run a Windows update that changes NT create file, it will change this number in this table also to point to it. So all your programs will continue to work. But this means you can modify this table. That's what rootkits did, and it's what firewalls used to do in antivirus programs for a long time until Microsoft got fed up with this, because this is more third-party people messing with things inside the kernel, which tends to cause problems. But this is called SSDT hooking. You can change this function, and then everything that tries to create a file will now run some different code than the code Microsoft intended. That's what you do. That's hooking. So the simplest way to detect SSDT hooking is just look at the SSDT, because the kernel is not very big. In this case, the whole kernel goes between 804 and 806 addresses. It fits in a relatively small area, so if you just list all the modules showing the SSDT table, which you can do with this command in WinDebug, you see all the addresses here. The left is the addresses. It goes up by 4 bytes every time, because it's just a series of 32-bit pointers. Here's all the pointers, and so you can see they all start with 82, because the kernel, all the real kernel calls start with 82, so this is an unhooked portion of the kernel. But when you find a hook, it will just stand out. You jump out the memory and see all of them start with 80, and here's one starting with 1F. So that's the one that's been modified. So this, you can do this, but it's extremely obvious that when people make that Windows API call, it's going to run some other code. This is what the rootkits did, and this is what the defense products did for a long time. So you can list modules. In the kernel, they're all drivers. And here's listings of a rootkit function. It's going to jump. This is the function that is going to load instead of doing NT create file. So what it's going to do is it's going to do some kind of logic, and sometimes it's just going to go to the real NT create file. So sometimes it will let the normal functionality happen, but some of this code will sometimes do something else. And this is what rootkits do. They'll have something like a certain folder that they decide you're not allowed to get in. So if you try to go in that folder, they will not let you in. But if you're going somewhere else, it'll let the normal operation of the computer go by. So by hooking these functions, you can fool more and more software. And simple rootkits, like some early Linux ones I worked with, would only hook like 10 calls. So in fact, they weren't very well hidden. You could use some command line functions to see the hidden stuff, but others were hooked. But a more sophisticated rootkit would hook more and more of them, so it's harder and harder for anything to find them. All right. Now, another thing to know about modern systems like Windows, and Linux for that matter, is it's all driven by interrupts. There's this thing, if you go into Task Manager, you'll see System Idle Process. Let me bring that up here. This is a pretty interesting fact about Windows. Okay. If I usually see it here. Let's see. System Idle used to be right there. Maybe they're not showing it anymore. But it used to be able to see it, how much CPU is being used. And you see it in Linux with top. Maybe it's not easy to see in Windows anymore. But anyway, the point is, when you're not doing anything, your machine is mostly just idle, doing nothing. It's waiting for a signal. It doesn't do anything until a signal happens, like the user presses a key or makes a mouse click, or something comes in on the network, or some kind of scheduled task goes off. That's interrupts. So everything is done by interrupts. It sits in an idle condition waiting, and then it gets a signal, then it processes the signal, then it goes back to the idle state waiting for another signal. So that's what's going on here. And so this specifies an interrupt service routine to run, and there's a table that describes these, the interrupt descriptor table. And you can see it here, and that should still be there. Let's see how it looks in this Windows machine I'm running, Bang IDT. bang IDT, dumping IDT, dumping extended IDT. Looks like it's not working very well. All right. Anyway, this is what it used to do in earlier versions of Windows. It looks like in the modern version, I'm going to have some kind of modification of this to see it. Anyway, all right, and there are some drivers there are tools you can download to make drivers and to make test drivers and load them and such. And that's what you have to do if you want to get into this in greater detail. And years ago, in earlier versions of Windows, I had students loading test drivers and examining them in the kernel and stuff, but it's not in the latest version of this course because it's much harder to do these days. And like I say, I haven't understood how modern kernel mode rootkits work. If I can figure them out, I'll add them to the projects. But it's much more difficult because Microsoft has added a lot more defenses in the kernel. Anyway, so here's, like I say, the later versions of Windows, the 64-bit BCD edit instead of boot.ini. And now they have PatchGuard, which prevents third-party code from modifying the kernel. Like I'm saying, so you can no longer modify the SSDT or the IDT. So this process of hooking that to control Windows is not the way it's commonly done anymore. All right. And also, driver signing is now enforced in all 64 versions of Windows. You can't just write a driver and put it in. It has to be signed with a public certificate. And I had one for a while. They cost like a couple $100 a year. And they identify you, and if you're caught writing malicious stuff, it'll get blocked. So that's what they do. They try to prevent you from adding drivers to the kernel until you prove that you're a fairly reputable company, to try to decrease the bugs in the kernel and the malware in the kernel. Anyway, let's look at the last Kahoot, which is 10D. All right. All right. All right, so which module is loaded and unloaded in a virtual machine? K-mixer is the one that you'll see loading and unloading, and it doesn't mean anything is wrong. All right, what's the normal function Microsoft components use to execute kernel code? It's sysenter is the function, the assembly code call to enter the kernel. All right. What's the most common object that was altered by the old-fashioned rootkits? The SSDT, that's the master table of the addresses of all the Windows API calls. Well, the kernel calls. All right, which one is not used in Windows 10? Boot.ini was used in Windows XP to control the boot up. It's replaced by BCD Edit in all later versions, including Windows 10 and 11. All right, and what do you do to run unsigned device drivers in 64-bit Windows? Yeah, you boot in a special mode with this flag, no integrity checks, and that will let you use an unsigned driver. They don't make it easy. They really don't want you doing it. All right, there. So, let me stop this recording.